Okay, November 2020, paper 4, variant 3. Hmm. Question 1. Figure 1.1 shows a trolley traveling down a ramp. Figure 1.2 shows a section of the tape. State how the dots on the tape show that the trolley was moving with a constant speed. How does this section of the tape show that the trolley was moving with a constant speed? Why was it moving with a constant speed? Because basically, yes, the distances between the dots are equal. Yes, you can say so. So we can say that the distances between the dots are equal. Okay, excellent. Next question. When the trolley reaches point P, the ramp is tilted so that the angle x is greater. Angle x is okay, great. Describe and explain the change in motion of the trolley. When the angle x is greater, so basically the trolley is or the ramp is somewhat like this. What's happening to the pen? Okay, so basically the ramp is somewhat like this. What happens to the speed? The speed increases, yes? The speed increases or it's accelerating. Why? That's the question. Why is it accelerating? Because there is resultant force. So whenever you say, whenever there's a question asking you, why does something speed up or why is there an acceleration? You have to say because there is a resultant force. So speeds up, speed increases. Why? Because there is a resultant force acting, okay, on the trolley. Another trolley is released from the top of the ramp. Figure or using figure 1.3, calculate the distance traveled in the first 0.5 seconds. How can I find the distance traveled? Is it speed times time? Nope, it's area under the graph, which is basically the area of a triangle. So it's half times base times height. Do I want the total distance traveled? Do you need the total distance traveled? No. Actually, you want only in the first 0.5 seconds. So you don't want all of the area. You only want up to 0.5 seconds. You need this small triangle. You need only this small triangle. So half times 0.5, half times the base, which is 0.5, times the height, which is 0.75. 0.75. This is a very small distance, definitely, which is around 0.19 meters. 0.19 meters. Again, do not forget the units, please. Figure 1.4 shows a metal ball at rest in a liquid of tube. The metal ball is released and reaches the terminal velocity at point x. So as the metal ball falls down, okay, at point x it reaches the terminal velocity. What is the terminal velocity? It is constant speed. Use ideas of forces and acceleration in your answer. What happens? How can it reach the constant speed? How can it reach the terminal velocity? Okay. Um, how can it reach the terminal velocity? Basically, initially, it had what force acting on it? Initially, it only had one force acting on it. Initially, it had the weight. So initially, only the weight, okay, or the force of the weight was acting on it, was acting on the ball. As it falls down through the water, it's not falling through air. As the speed increases, okay, initially the only force acting on it was the weight. As the speed increases, you have to say that as the speed increases, what happens, or type of hmm, what type of force increases? The resisting force increases. Okay, resisting force increases. Resisting force increases, therefore the resultant force acting on the ball, the resultant, okay, force decreases. Resultant force keeps on decreasing, which is the force that accelerates the ball. Force equals ma. Resultant force decreases, and acceleration also decreases until which point? Until at point x. What happens until the weight is equal to the resistive forces? In this case, you can call it the water resistance or upthrust or whatever. The weight is equal to the resistive force, and therefore zero resultant force, which means that it moves at a constant speed, or okay, constant speed, or in other terms, you can say that it is moving at the terminal velocity. Okay, terminal velocity. Okay. Okay. Yeah. Next question. You have water, okay, and a ball falling. The ball falls over the edge. The distance is, or the height is 115. The mass is 160 grams. Calculate the vertical speed. Air resistance may be ignored. Air resistance may be ignored. So how can I find the speed? This is basically kinetic energy. This is kinetic energy. So for this question, you can say that all of the gravitation potential energy is converted to kinetic energy. All of the gravitation potential energy is converted to kinetic energy. So, do I actually need the speed? Sorry, do I actually need the weight or the mass of the ball? No, you do not need the mass of the ball. You need the mass for the next question, B, but you do not actually need the mass for this question. Why? Because you will say that the kinetic energy is equal to the gravitational potential energy. Gravitational potential energy. Or in other terms, half mv squared is equal to mgh. We can cancel out the mass with the mass, so half v squared is equal to gh. I told you before, how can we find the velocity? Okay, how can we find the velocity? Basically, velocity equals square root 2gh. Square root 2 times the g, which is 9.8, times the height, 115. Okay, square root 2 times 115 times 9.8, 47.47. So you can say 47.5 meters per second. 47.5 meters per second. This is the final speed of the ball right before it hits the ground, right before it hits the surface of the water. Calculate the vertical momentum of the ball as it hits the water. Vertical momentum, so P equals momentum equals mv. The mass of the ball is 160 grams. 160 grams. This is definitely not the SI unit. We have to convert it to the SI unit, which is 0.16. Mass is 0.16 divided by 1,000 times the velocity 47.5. So 47 times 0.16, giving you a momentum of 7.6. But the other question is, what is the unit of the momentum? Unit of the momentum. Yes, kilograms dot meters per second. Kilograms dot meters per second. Or Newton seconds. Yes, Newton seconds. Speed is a scalar quantity. State one other scalar quantity. Any other scalar quantity would do. You can say mass. You can say temperature. You can say distance. Velocity is a vector quantity. One other vector quantity. Momentum. We just found the momentum. Okay. Acceleration. Force. Yes. Figure 3.1 shows a model car traveling at a constant speed in a flat circular track. The speed is 0.3. The car travels 3.9 meters. Calculate the time taken for the car to complete one revolution. Time. You have distance, you have the speed. Okay, you have the distance and the speed. So time equals distance over speed. Time equals distance over speed. Honestly, I do not know why they gave you this answer, this question. It's a really easy question. distance is 3.9, and the speed is 0.3, which is gives you a time of 13 seconds. This is the total time taken to complete one complete rotation. Next question. On figure 3.1, figure above, figure 3.1, draw and label with the letter F any arrow to show the resultant force acting on the car. If this is a car moving in a circular motion, where is the resultant force acting? You have to say that the resultant force acting on the car is towards the center. The car is moving. Yes, so the resultant force is towards the center. F, this is the centripetal force. Yes, it is the centripetal force. The speed of the car increases, and at point P, the car does not stay on the track. So, just in terms of the force acting on the car, why the car does not stay on the track at point P? Why doesn't it stay on the track? The speed increases. As the speed increases, what happens? What happens is that the car could slip, okay, or that the resultant force, there will be a resultant force of the car, or uh, you can say that they are not yet, they are not anymore balanced. The resultant force, or the force acting outwards, is now larger than the force acting inwards, right? You might say that, okay? You might say that. So the inward force, the centripetal force, is not enough. The centripetal force is not enough. You need a stronger centripetal force. The centripetal force, okay, force is not sufficient. You need a larger centripetal force, which is true because as you increase the speed, this centripetal force is required to keep the car in motion or to keep the car in a rotation. Okay, it would increase. Yes. On figure 3.2, draw and label an arrow with the letter S to show the direction of the motion of the car as it leaves the track at point P. At point P, the car will leave the track. The car will leave the track. In which direction will this car move? That's the question. In which direction will this car move? Will it move in a circular motion, or will it move? How will it move? It will move always perpendicularly. It will move in a perpendicular motion to the force. So if the force was in this direction, the car will move perpendicularly, or we can say tangent to the circle. Tangent to the circle. How did I know that the car is moving in this direction? You can say it was either moving in this direction or in the other direction. So if you assume that the car was moving in the other direction and you wanted to draw another arrow moving in this direction, it's okay. It is okay. Either arrow will do the trick. But the arrow or the line has to be tangent to the circle, or it has to be perpendicular to the force, to the centripetal force. Okay? Hmm. Yeah. Question 4. Figure 4.1. The circles represent the molecules of different states of matter. Very easy. A is a liquid, definitely. B is a solid, and C definitely a gas. Explain in terms of forces between the molecules why gases expand more than liquids when they have the same rise in temperature. Assume that the pressure remains constant. Okay, whatever. Why do gases expand more than liquids? Two things. You have to talk about two things. You have to talk about the forces and you have to talk about the distances. Yes. What are the forces between the molecules in a gas? Forces in the gas is much weaker. Okay, forces between molecules in gas is weaker, and the distances between molecules as well, between molecules in gas, is much larger. Hmm. Figure 4.2 shows a cylinder and a piston. The volume of the gas in the cylinder is 3,400 centimeters cubed. The pressure is 0.9 times 10 to the power of 5. The piston is moved to the left, and the new position increases the pressure to 2.5 times 10 to the power of 10. And calculate the new volume. Okay, that's easy. How can I find the new volume? You have an equation. PV is constant. PV is constant. So basically, P1 V1 is equal to P2 V2. We want to find V2. We want to find V2. It's a very simple equation. All you need to is plug in the numbers. So V2 would be equal to P1 V1 over P2. Pressure 1 was 0.9 times 3,400. 0.9 times 3,400, 0.9 times 10 to the power of 5, 0.9 times 10 to the power of 5 over 2.5 times 10 to the power of 5. So basically what happens to a volume, yes, volume will be around 1,200 centimeters cubed. You do not need to convert the volume, no. You do not need to convert the volume. The gas in the cylinder is now heated. The piston remains fixed in the same position. The piston is now fixed in position, and as you heat the gas, as you increase the temperature, state and explain in terms of molecules any change to the pressure of the gas. As you heat up the gas with a constant volume, with a constant volume, what happens? Pressure? Yes, pressure increases. Why does the pressure increase? Okay, we need to talk about pressure increases. Pressure increases. Why? Because the molecules are now moving faster. They are hitting the walls more frequently, more oftenly. They are hitting the walls with a greater force. Okay? So molecules move faster, hit the walls harder, and more frequently. And more frequently. Okay, not bad. Hmm. Now we have two plates, a shiny plate and a dull black plate with a radiant heater in the middle. You have a cork which is attached to each of these plates using a piece of wax. Metal plate A is shiny, B is okay. The wax is solid and has a melting point of 37 degrees. State and explain what happens to pieces of cork after a few minutes after the heater is switched on. Which, which cork will fall first? That's the question. Which cork will fall first? Definitely the one on the dull black. Why? Because the dull black surfaces are better. Can you say this question? Can you say emitters? Hmm. Can you say that dull black surfaces are better emitters? No. Why? Because in this case they are absorbers. They are absorbers. So we need to say that the cork on plate B falls before A. Why? Because the dull black surfaces dull black surfaces are better absorbers of what? Of infrared radiation. Of infrared radiation. Okay? Okay. Give the name of the method of transfer in these solid metals. Hmm. Inside the solid metals. He didn't say from the heater to the solid metals. No, he said in the solid metals. So in solid metals, it has to be by conduction. By conduction. Okay. Yeah. Sound waves consist of compressions and rarefactions. Give your explanation in terms of spacing in the molecules and pressure. Spacing of the molecules and the pressure. So basically the spacing in the compression. What happens to spacing? Molecules are closer together. So the molecules are closer together and the pressure increases. The pressure increases above the atmospheric pressure, to be honest. Okay, increases. It is greater than, slightly greater than the atmospheric pressure. Okay, what about the rarefactions? Okay, the molecules are further apart, and the pressure decreases. Again, lower, or it is now less than the atmospheric pressure. A musical instrument emits a sound at a frequency of 4.4. Speed is 340. Can I find the wavelength? Yes, wavelength equals speed over frequency. But I have to take care that the frequency is in kilohertz. So the speed is 340 and the frequency is, I have to multiply this by 1000. Okay, sorry for that. You have to take into consideration that the frequency is in kilohertz, so you multiply it by 1000, and therefore the frequency is 4400 hertz. 340 divided by 4400 would give you a wavelength of, let's calculate it, 0.077 meters. The frequency of the sound emitted by the instrument is changed to 5.1 kilohertz and the amplitude is increased. Both of them increase. What happens to speed and what happens to the wavelength? That's a really nice question. As you increase the frequency, as you increase the frequency, what will happen to the speed? Hmm. Actually, the speed doesn't change. Speed doesn't change. Why? Why doesn't the speed change? Because you're not talking about a different. You're talking still about the speed of sound. Speed of sound is 340. The speed of sound in air, to be more specific, is 340. So whenever I'm talking about the speed stays the same. What happens if the sound moves from air to liquid, for example? Oh, then the speed will increase. But for this case, the speed remains the same. Okay. What happens to wavelength as you increase the frequency? Speed equals wavelength times frequency. As you increase the frequency, what happens to the wavelength? The wavelength, yes, it decreases. Wavelength decreases. Okay. Two uses of infrared radiation. Infrared radiation. What do we use them for? Most commonly, we use them for the remote controllers and the, yes, and the thermal imaging. Yes, it is correct. Thermal imaging is correct. Okay, you can say intruder alarms as well. Okay, so you can say the remote controllers, and intruder. Something is wrong. Okay, intruder alarms. X-rays are used in hospitals to treat patients. Suggesting explain three precautions for the safe use of X-rays. We have very simple precautions. First of all, you need to use some sort of protective barrier. Okay, yeah, shielding. Okay, so let's write down the shielding or protective barrier or protective barrier. What else? You have to, yes, reduce the time of contact. Okay, reduce the time of exposure. Hmm. Also, what should I do? Increase the distance between you and the source. Okay, reduce time of ex um reducing the time of exposure, and last but not least, you can say increasing the distance. Increasing the distance. Okay. State the speed in vacuum of microwaves and X-rays. State the speed in vacuum. It's the same speed basically. So it is the same speed, which is 3 times 10 to the power of 8 meters per second and 3 times 10 to the power of 8 meters per second. State a possible frequency for an ultrasound wave. Whatever frequency above what value? Huh? Whatever frequency above, to be exact, 20,000 hertz. So if I say 21,000 hertz, would that be correct? Yes. Mister, can I say 20,001 hertz? Okay, it would be correct. But why? Why would you do that to yourself? 25,000 hertz. Okay. Hmm. Next question, question 8. You have an electrical circuit, you have a current in the circuit, and you have, find the current in the circuit. The reading on the voltmeter is 3 volts, and the resistor has a resistance of 4 ohms. Can I find the current? I equals V over R. So basically 3 over 4, which is 0.75 or 0.75 amperes. Okay, 0.75 amperes. I guess that's easy. 0.75 amperes. What is the figure 8.2 shows the same circuit with one component reversed. What is the reading? What is the reading on the voltmeter now? Is this circuit operating? Is this circuit operating? No, it's not operating. Why? Because this is a diode. So as the current passes through the diode, it won't be able to pass. It's actually blocked by the diode. So the reading is zero. Explanation: because the diode will not allow the current to pass. Okay, diode blocks the current or doesn't allow it to pass. Diode is reversed. Definitely, this has been removed from the syllabus. So part B and C are all cancelled. They're all cancelled. Question 9. Electrical power is produced in a power station by an alternating generator. Explain why the electrical power is transmitted at a voltage of 400,000 volts instead of 22,000 volts. When you produce the voltage and it's 22,000 volts, that's already a very high voltage. Yes, a very high voltage. How can I, or why do I even increase the voltage above 20,000? Why do I increase it to 400,000 volts? As you increase the voltage, what happens to the current? What happens to the current? The current is lower. Yes, the current decreases. So basically, the amount of energy lost decreases and the power lost decreases. So you can use thinner wires. That's it. Okay. As the voltage increases, what happens to current? Current decreases, and therefore the energy lost. And you can also say that the power decreases. Power decreases, and you can use, well, you can use thinner wires. Thinner wires. A computer containing a transformer. Okay, you have a transformer inside the computer. Input voltage is 240. The output voltage is 20. The output current is 2.3 amperes. The efficiency of the transformer is 90%, which is 0.9, which is 0.9. Calculate the input current to the transformer. Okay, okay. Don't panic. Do not panic. Can I find the input current without it being 90% efficient? Can I find the input current, for example, if it was 100% efficient? Yes. How can I find it? Okay, this is a 5-marker question, which is a lot. How can I find it? Well, the equation we use is what? VP IP equals VS IS. Because we have current and input power is equal to the output power. Primary power is equal to the secondary. Anyway, so what is the total voltage, the power? It's 240. That's the input. The output is 20. So you need IP. You need to find an input current. The output voltage is 20 and the output current is 2.3. Can I find the IP? Yes, well, IP would be equal to 20 times 2.3 divided by 240. So let's calculate this. 20 times 2.3 divided by 240. This would give you a current of 0.19 amperes. Is this the final answer? No, it's not the final answer. It is not the final answer. Why? Because it's 90% efficient, meaning that some of the energy or some of the power was lost. Some of the power was lost. So actually, this reading has to increase. It needs to increase by how much? By 10%. Or in other terms, we can say 0.19 divided by 0.9. 0.9 divided by 0.9 is 0. Around 21, I guess. 0.19 divided by 0.9 is around 0.21. Yes, exactly. This is the input current. Okay, question 10. You have a relay, circuit B and circuit A. With some contacts, the switch in circuit A is closed. As you close the switch in circuit A, what happens to the circuit? How does this operate the motor in circuit B? How does this If you look closely, you'd find that these contacts are now not touching. They are not in contact. What happens? As you switch on the circuit in A, as the current passes through the coil, okay, as the current passes through the coil, what happens? A magnetic field is created. A magnetic field, a magnetic field is created. As this magnetic field is created, what happens? It attracts this soft iron armature. Attracting the armature. As it's attracted, as the soft iron armature is attracted, what happens? It kind of pivots upwards. Kind of pivots upwards, and therefore the contacts touch. Okay, so it pivots upwards, and the contacts touch. That's it. Pivots upwards, and therefore the contacts touch. The switch in circuit A is opened. The soft iron armature is replaced with a steel armature. Switch is closed. State what happens when the switch is then opened. So you have this, you open up the switch, you remove the iron bar, you replace it with a steel bar, you close the switch, and then after some while, you open the switch again. What happens? Why is this a problem? Why would this be a problem? The problem would be that uh, the steel is a permanent magnet. The steel will be magnetized. The steel will be magnetized. So basically, if you open the switch or close the switch, it wouldn't matter. Why? Because it will remain magnetized. The contacts will remain touching. Okay? They will keep on. Why? Because it is still magnetized. Okay? So as you open the switch, the question is, what happens when you open the switch again? So the motor will remain on. The motor will keep on. The circuit B will remain operating. Okay, will keep on operating. Okay. Circuit B hmm, will not switch off. Why won't it switch off? Will not switch. Why won't it switch off? Because the steel is still magnetized. Okay, the steel is still magnetized. Okay, yeah. Okay, question 11. Figure 11.1 shows the beam of alpha particles, beta particles, and gamma rays. On figure 11.1, draw the paths of each of these. Okay, that's easy. Alpha, beta, and this is it's an electric field. This is not a magnetic field. The magnetic field would have been a bit different. This is an electric field. It's quite easy. Alpha, for example, alpha is positive, so it will deflect, it will move towards the negative plate. Okay, in quite a weak deflection. It will take a long time to, this is alpha, it would take a long time to reach the negative plate. Beta, It would have a strong deflection towards the positive plate. Why? Because it's negatively charged. But what about the gamma? It will continue in a straight line. Okay, gamma would continue in a straight line. Why? Because it's uncharged. The gamma is uncharged. State and explain one practical application of gamma rays. Gamma rays, one practical application is what? We have several applications, but you can say, for example, cancer treatment. Okay, cancer treatment. Why can we use it in cancer treatment? Because it kills the cancerous cells. In cancer treatment. Why? Because it kills the cancerous cells. That's it. Okay.